Hello everybody, I'm Ferrett from the University of Reading. Today I'm going to be talking about some of the work I've been doing as part of FORCI, which is a collaborative project between 3 UK universities and the Met Office. My work focuses on evaluating convection permitting ensemble forecasts of precipitation over Southeast Asia. I'll just introduce you to the ensembles that I used during this work. There are a number of ensembles at varying resolutions over various domains. So the domains are shown in this figure here, where the solid line indicates the domain for a 4.5 kilometre ensemble, the dashed line indicates the domain for the 2.2 kilometre ensemble. So I'll refer to these domains as Malaysia domains, these domains as Indonesia, and these domains as the Philippines. Each domain has 4 ensembles: the 8.8 kilometre convection permitting ensemble, the 8.8 kilometre parameterized convection ensemble, the 4.5 kilometre convection permitting ensemble, and the 2.2 kilometre convection permitting ensemble. Each ensemble has 18 members, and the forecasts will run for 6 months spanning October 2018 to March 2019, out to a lead time of 120 hours, except for the 2.2 kilometre, which has a lead time of 60 hours. The work that I'll show was focused on 3-hourly accumulations of precipitation, which are compared to GPM iMerge, and the results will mainly focus on the 4.5 kilometre CP ensemble, initialized at 00Z, and then towards the end there will be a comparison of all 4 of the ensembles for the Malaysia domain. In this figure I just show how precipitation intensity is represented in the ensembles for each of the domains. This is the result for the 4.5 kilometre ensemble. I have the 95th percentile of precip as a function of lead time. The dashed line in this figure shows the value for GPM, and the solid line shows the forecast. The colour of the lines indicates the domain that was looked at, so the black is Malaysia, the red is the Philippines, and the blue is Indonesia. If we take a look at Malaysia first, you will see that in the first sort of day and a half of the forecast, precipitation is overestimated by the forecast. In later lead times, precipitation is underestimated in comparison to GPM. For Indonesia and Philippines, precipitation is underestimated for all lead times. You'll also notice that precipitation has a strong link to diurnal variation. So we see a peak in the local early morning and a peak in the local evening, shown here. One thing to note is that in the forecast, the relative strength of the peaks are not that well captured. So in GPM, the strongest peak occurs in the morning time, whereas in the forecast, the strongest peak occurs in the afternoon. So the relative strengths of those are not that well captured. Today I'll be showing you results from a fraction skill score analysis of our ensemble forecast. So this slide just details exactly what the fraction skill score does, but essentially in order to calculate it, we convert our data into fractions of the number of points within a neighbourhood of a certain size which exceeds a rainfall threshold. So here I have a schematic which shows you what that means, where I have an example of radar data on the left and an example of forecast data on the right. This schematic was taken from the Robertson-Lean paper describing the method. And the grid points are shaded based on whether the rainfall in a certain grid point exceeds the threshold. Comparing grid point for grid point, it looks like the forecast is not doing a very good job of replicating the radar. But if we look at a neighbourhood of grid points, so this larger square here shows a 5 grid point by 5 grid point neighbourhood, each of the data sets actually shows 6 out of 25 of the grid points exceeding that threshold. So then we would conclude that the forecast is actually doing a very good job of replicating this radar data. And essentially the fraction skill score looks at the ratio of the error between the observed and forecast fractions over a full domain of neighbourhood length n over the maximum possible mean squared error from these two fields. And the takeaway is that the fraction skill score of 1 means that the forecast is perfect, and if it's 0, it means that the forecast is bad. The benefit of the fraction skill score is that it can be calculated for varying neighbourhood sizes. So here I have a schematic figure which shows the FSS as a function of neighbourhood size or spatial scale. Generally, an FSS exceeding 0.5 means that the forecast is considered useful. So this gives us a target skill to exceed. And then essentially any spatial scale at which the FSS exceeds this target, these would be considered the spatial scales that the forecast is useful. Here is the result for the FSS analysis for the 4.5 kilometre Malaysia ensemble forecast. Here I have the FSS as a function of spatial scale on the x-axis and lead time on the y-axis, so the shading being the FSS. As I mentioned, the goal is that FSS exceeds 0.5. So the contour of this 0.5 value is shown in red. And the first thing that you will notice is that the skill tends to vary significantly with the diurnal cycle. And so the takeaway of this figure is that the closer to the left that this line is, the more accurate the forecast is at smaller spatial scales, so therefore the better the forecast. And you'll see at 12 UTC the skill is higher, and at 24 UTC the skill is lower. So these correspond to the times of day where rainfall is over land and then when rainfall is over ocean. So we conclude from this and some additional analysis that the higher skill occurs when precipitation is more constrained by orography. Because of this strong relationship with the diurnal cycle as well, we also compare this result to a fraction skill score analysis of a climatology forecast shown by the blue line. So you can see that the blue line is much further to the right, and therefore the ensemble forecast adds a great deal of skill to one purely based on climatology, suggesting it's not just the diurnal cycle that contributes to this skill. Here I switch to the result from the Philippines analysis. Now the rainfall in the Philippines is not as strongly driven by the diurnal cycle as it is in Malaysia and Indonesia, and you can see that in the skill results. So there aren't these large variations depending on the time of day. And also comparing it to the climatology forecast, which in this case you can hardly see off the chart of the spatial scale. The ensemble forecast adds a lot of value compared to that climatology forecast, suggesting that the diurnal cycle has a very small role to play in the forecast scale. Results in Indonesia were very similar to that in Malaysia, simply because the diurnal cycle also plays a large role in that region. Finally, I have a comparison of the skill of all four of the ensemble forecasts that I mentioned at the beginning. This figure just shows the FSS at a spatial scale of 140 kilometers as a function of lead time. Each coloured line represents one of the ensemble forecasts. Generally, the takeaway here is that resolution has relatively little impact in forecast skill. So all three of the CP ensemble forecasts shown by the black, blue and red lines have very similar skill compared to how more computationally expensive these higher resolution ones are. The thing that does make more of a difference is convection parameterization. So this is shown by the parameterized convection ensemble in the green line, comparing this to the 8.8 kilometer CP ensemble in the red line. You can see that there is quite a loss of skill in the parameterized convection version of that ensemble, suggesting that this has more impact. But this is region dependent, so the result in the Philippines is that actually the parameterized ensemble has a slightly higher level of skill compared to the CP ensemble, and this is probably because the rainfall in the Philippines is driven more by large scale conditions but that's something that we're looking at in more detail in future. Here is the summary. I won't go through this in the interest of time. Please read through it on your own time. If you have any questions, email me. Here is my email address. The results from this work were also recently published in Weather and Forecasting, so if this was interesting to you, please do check it out. It's online now, or you can email me for a copy if you don't have access to that journal. So thank you.